My name is Stefan Kollet. I'm from the Research Center Jülich, and I'm going to talk today about some basic concepts and some advanced concepts of modeling interactions of agricultural systems with the terrestrial water and energy cycle. So the plan for the next 30 minutes is to take a tour from groundwater across the land surface with agricultural vegetation crops into the atmosphere and learn about the different processes, have a look at some of the theory or relevant theory and equations, and maybe most importantly to understand some of the major challenges and assumptions in simulating the terrestrial systems and interactions with vegetation and specifically with crops. Okay, so this cartoon here shows, let's say, conceptually, the terrestrial water and energy cycle, really from the bedrock to the top of the atmosphere. So we have groundwater flow, we have base flow, convergence along river corridors and interaction with surface water. We have continental discharge even along the shelves here. We have interactions with the variably saturated zone, infiltration from the land surface. We have interactions with vegetation. We have complex transport, turbulent transport of momentum, of energy and moisture between the land surface and the atmosphere. Then, of course, also we have the atmospheric processes related to radiation, related to cloud forming processes, precipitation, also snow and ice. And then, of course, we have the anthropogenic impact. We have, for example, here agricultural plots at different scales, interacting with the terrestrial water and energy cycle. So basically, depending on the terrestrial water energy cycle, and then also impacting, let's say, the energy cycle at the regional, also to the continental scale. And this is what we're going to look at more closely today. So what characterizes the system? We have variability in fluxes and states at all space and time scales, really from sub-centimeters, millimeters to thousands of kilometers, and also from seconds or sub-seconds to hundreds or even thousands of years if you talk about geologic timescales. And of course, these interactions are two-way, they are non-linear, and they are actually happening between all compartments, again, at all space and time scales. So why do we want to model this system? Well, the ultimate goal is, of course, to make predictions across scales. So we really want to predict, we want to be prognostic from the continental scale, across the regional scale, down to the local scale, really the field, or let's say a number of different fields. And to do that, actually, we have to tackle one major challenge. We have to establish also the current state of the system. So we have to know in which state the system is right now and how it got there in the past. And to do that, we actually merge our simulations or our models with observations via data assimilation technologies. I believe you already heard about this also in these lectures. And then actually, if we know the current state, we can start spawning predictions or forecasts at different time scales, let's say hours, multiple days, weather time scale, and up to the climate time scale or even longer. Okay, so this is one of the major motivations actually to model the terrestrial system. And of course, we want to understand the impact of human interventions, such as agricultural fields. Okay, as I said, we have interactions across all time and space scales. Just to give you an idea about the time scales we are dealing with here. So you see here along the columns, you see the different fluxes of the terrestrial system, the storages, and the residence times of water molecules in the different compartments: groundwater, surface water, soil water, and atmosphere. These fluxes you see here, these are global average fluxes. And you see here, for example, groundwater has a relatively small flux of about 13,000 square kilometers per year. In comparison, the atmosphere has a very high flux of close to 600,000 cubic kilometers per year. Why is that? Why do we have this huge difference in fluxes? Well, the atmosphere is extremely dynamic, can store only very small amounts of water. You see that here in comparison to the groundwater storage, which is very large. And that leads then to large differences, for example, of residence times of water molecules in the different compartments. So, for example, in the atmosphere, a water molecule maybe resides a few days, maybe 10 days. In contrast, in the groundwater compartment, water molecules live there for a long time. Let's say on average, maybe thousands of years, but this distribution of these residence times is extremely wide, from let's say hours to thousands of years even. Okay, so this gives you some idea of the timescales and dynamics we have to deal with if we want to model the terrestrial system, including also interactions, for example, with agricultural systems. Okay, so these are average fluxes, global average fluxes. However, the dynamics that you see here really also hold at the regional, even at the local scale. Okay, first, when we want to model the system, we start with conceptualizing it. So we always have to simplify because of the tremendous complexity. So this would be a conceptualization of the system, of the different compartments that are interconnected, just reflecting the major fluxes we have to account for. So at the top of the atmosphere, incoming solar radiation that drives really the terrestrial cycles. At the top, we have here precipitation, we have evapotranspiration, we have the difference of both leading to infiltration into the subsurface. Maybe we have again wood water uptake leading to evapotranspiration. We have groundwater recharge, groundwater flow and transport towards the river corridors, base flow to surface water discharge, continental discharge to the oceans that close the water cycle, and then of course advection, bringing back the moisture from the oceans back to the continents. Okay, to understand why we want to model the system in an integrated fashion, meaning really from bottom to top, we can have a quick look at the very basic balance equations, water balance equations. And we start here in the subsurface. So we have total subsurface storage, land surface storage here on the left hand side. Then we have precipitation here as the source, evapotranspiration as the sink. We have a continental run of R also as a sink, and here we have the subsurface flow of water here as the divergence term. Okay, I think this is quite intuitive. We can write something similar for the atmosphere. So we have atmospheric water storage here on the left-hand side. We have the atmospheric transport here as the divergence term, and now precipitation really appears as a sink, of course, and evapotranspiration really appears as the source. So because we have seen that before in the previous slide, the atmosphere is extremely dynamic, can store only a very small amount of water. So these changes in water storage in the average in the atmosphere, they average out quite quickly, let's say on the order of months. And then the atmospheric divergence actually equals the continental sink. So here we have the transport equals the sink, the precipitation, evapotranspiration, which makes actually the continental sink for atmospheric water, meaning really over the continent, usually precipitation is larger than evapotranspiration. Thus, the continent constitute a sink for atmospheric water. Okay. And now what we can do is we can substitute the sink source terms on both sides, and we arrive actually at a very straightforward integrated mass balance, really from bottom to top, where we have the storage term of the land surface, subsurface on the left-hand side equals the atmospheric transport and the continental runoff. Okay, so of course, this is a very simple mass balance equation. It's hiding all the complexity actually in the different terms, okay? But what it means really is that as soon as you change some of these terms here, like precipitation, or you change evapotranspiration because of human interventions, for example, irrigation, you know, of agricultural systems, you're going to change the atmospheric transport, and you're going to impact the water balance from bottom to top. And of course, we also solve for the energy balance here, which I put here on the left-hand side. Net radiation equals latent heat, which is actually evapotranspiration, sensible heat, and the ground heat flux. I will focus today on the water balance terms, so we will not see that equation again, but remember please that this equation, of course, is intrinsically coupled to the water balance. Okay, so as I mentioned, what's the plan? We go from bottom to top. We start in the groundwater compartment and make our way up, let's say, to the top of the surface layer at the land surface. So that's where we stop today. We will not talk about transport in the free atmosphere. And we start right now, we start really here in the groundwater compartment. And the first thing we do is we have a look at a cross-section in our subsurface to see where our groundwater compartment sits and what are the dominating processes here. So we have here a cross-section through a shallow aquifer, that's how we call, let's say, the groundwater compartment, which is here connected to surface water. And you see here base flow originating from recharge zones, you know, flowing towards discharge zones along the river corridors and discharging to the continental rivers. That could be, for example, a cross-section through the Rhine Valley here that you see basically when you go along the Rhine. Okay, so we have here infiltration and recharge zones from the land surface, but we have also, of course, interactions upwards. So we have capillary wise towards the root zone, root water uptake, evapotranspiration. And when we look into the micro scale, when we look really into the pore space, we see that we have the matrix. We have the matrix filled entirely with water in the saturated zone. We have a free water table. We have a capillary fringe where we have tension saturation. Then we can have basically capillary rise through the pore space up to the land surface, interacting with the vegetation and also agricultural systems. Okay. So now if we want to model this flow and transport in the groundwater zone, we have to do one thing first. We have to write out two equations. We need a continuity equation that we have here on top. That looks complicated, is actually very simple. On the left-hand side, again, we have a storage term. On the right-hand side, we have the divergence term that is reflecting the flow. And then we have another term here, which is the general source and sink term. This is one equation we need. Now we need a second equation, and that is actually the movement equation that we can combine with the continuity equation to actually simulate the flow. Okay, we actually know which kind of movement equation we are supposed to take, which is really Navier-Stokes, right? But we have to make a decision here already, and that is a very difficult decision. So at which scale do we want to simulate the flow? Do we actually want to simulate the flow at the pore scale? So really, you know, tracking the water molecules through this porous space, where we have to take into account the shape of the matrix and the shape of the pores, or do we want to do an upscaling to the macro scale to, let's say, some continuum scale? And if we want to do the second, well, then we have to really understand how we are supposed to do the upscaling. So think about this a little bit, but I think very quickly we realize, well, we are actually not able to do the micro scale flow and transport. Why? Because we would have to know the system at a very high detail. And of course, we need extremely high resolution over very large scales, which is computationally not really tractable. So we have to upscale that problem to the macro scale. And what we could do, for example, we could do a very rigorous theoretical upscaling by taking Navier-Stokes, integrating all the laminar boundary layers here around the grains, and then arriving at some upscaled movement equation. Well, this is very difficult, but it can be actually done for some very engineering systems, from the lab. But in reality, it's very difficult because we know very little about the pore geometries and the matrix geometry. Okay, so we resort actually to an empirical upscaling, and that comes from a guy with the name Darcy, you probably heard about, who actually performed laboratory experiments at the end of the 19th century. So what he did, he took a column, he filled it with dirt, with soil, sediments, and he saturated the sediments, okay? And then he applied a hydraulic head gradient across the column from H1 to H2, and he measured the flow. And then he varied this gradient and simultaneously measured or monitored the flow. And he found actually that there is a linear relationship between the gradient in the hydraulic head and the flux over actually a very wide range. And he basically proposed a proportionality constant that is relating the flux with the gradient that we call the hydraulic conductivity. Okay, and this hydraulic conductivity actually does the upscaling for you from the pore scale to the macro scale. So now we have a continuity equation, and now we have a simple movement equation, which is the Darcy flow equation here. And now we can combine the two. Here we have our continuity equation, the storage term here, expressed in terms of the hydraulic head as the sum of the metric potential and the elevation potential. And we can combine this now with the Darcy flow equation to actually simulate flow in the groundwater compartment. What else do we need? Well, we have to inform our equations with the values of our physical parameters, for example, the hydraulic conductivity, and for example, also here the compressibility, the specific storage of the system. Well, let's focus on the hydraulic conductivity for now. So this, of course, is a characteristic, let's say, of the fluid we are talking about. This is in this case water, and of course of the matrix or the sediments in the subsurface or the soil, right? So we have to provide our flow equation with this hydraulic conductivity everywhere in the domain we want to simulate. And we have to do that across scales again, let's say from meters, let's say to 20 meters here, what you see here in the outcrops. And what we see already here in the picture is, well, the system is highly heterogeneous, right? So this hydraulic conductivity varies greatly from one place to the next. So, and thus we have to find this value. And then if we use different resolutions, we actually have to upscale this hydraulic conductivity, let's say from this grid size to that grid size or to the next grid size. So we have to find, on top of upscaling the flow equation, we have to find a way how to upscale or downscale our hydraulic conductivities. And in this case, there are very rigorous methodologies how we can do that, but also empirical approaches. Okay, now we basically have everything ready for groundwater compartment. Well, we have to now connect to the variably saturated zone. How do we do that? Well, in this case, our continuity equation and our flow equation are almost the same, except in the continuity equation, we have to take into account variably saturated conditions here. So the saturation of the soil or the sediments, because now we not only have matrix and water, we also have air. This is one thing we have to take into account, and this is dependent on the matrix potential or vice versa. On top, we have to take into account the dependence now of the hydraulic conductivity on the saturation of the soil, or let's say the matrix potential of the soil, meaning if the soil becomes drier, the hydraulic conductivity decreases. Okay, so we have now all equations we need, but we need on top some functionals for the dependence of the hydraulic conductivity on the saturation and the saturation on the matrix potential. So we do that again in the lab. We perform experiments in the lab where we use soil probes that we saturate and then we dry them, applying a suction at the probe, and then developing these water retention curves you might have heard about. So this is plotted here. Here we have saturation on the y-axis. The soil here, if it's 1, it's fully saturated. If it's 0, it's entirely dry. So we increase the suction, so we dry the soil, and what we observe here is this sigmoidal shape of this curve going from fully saturated to completely dry. And so we fit a function to this, which you might have heard also about, which is the Van Genooten function or the Brooks and Corey function that we can use in combination with our continuity and movement equation to solve for flow and transport in the subsurface from groundwater to the land surface. This is shown here. So what do we do here now on top? Well, we can apply simple flux boundary conditions, or we want to connect really to land surface processes such as vegetation here shown in terms of like simplified crops. Okay, so now we are at the surface and we have a major problem here. And this is the turbulent transfer of energy moisture from the land surface into the free atmosphere, which is not only important, but this is making up really the flux and transport there. And this is indeed a real challenge. Why? Because we are indeed not able to simulate turbulence at all scale, let's say at the large scale, at the large eddies where the energy is generated, and the small eddies where the energy is dissipated. So again, we resort to an empirical approach to observations and a dimensional analysis. So what we observe usually is that we have a logarithmic profile above a rough surface, in this case a canopy. This here shows the wind speed, where the wind speed actually goes to zero right at the rough surface and then increases logarithmically away from the rough surface. Why is that? Why do we observe that profile? Well, in terms of wind speed, we have a flux of momentum towards the rough surface, and here this momentum is dissipated into heat. But this profile not only holds for wind velocity, for the transport of momentum, it also holds for moisture or specific humidity, and it also holds for energy. And if you do a dimensional analysis, we can actually derive that profile, where we have here the evaporation flux. We have different terms here or contributions for mechanical turbulence described by the Kalman constant and the friction velocity. We have a geometric factor here, which is the displacement height. It's kind of a datum for the height of the plants. This is, for example, a parameter we measure in PhenoRob over the fields with LiDAR in different projects. Then we have, as I said, the humidity profile, and on the right-hand side, we have the atmospheric profile. This is actually the contribution of the thermal turbulence to our transport. Okay. So, and this holds also for energy. It's basically the same equation. It's just that here, instead of the specific humidity profile, you have the temperature profile, and here we have the sensible heat flux. Okay, this looks kind of complicated. It's an ordinary differential equation, but we can easily rewrite that in something that is actually fairly simple. Before we do that, we have to realize one major assumption here. And this major assumption is that the transfer of heat, energy, moisture, and momentum only happens in 1D. It's really 1D isolated columns in the vertical direction. So we cannot simulate lateral transfer across that land surface based on that theory. And currently there does not exist a robust theory that actually is able to do that. So this is one of the major assumptions. And the assumption roots in thinking that really here the land surface is statistically homogeneous, which requires a certain space scale on the order of tens or hundreds of meters. So as I said, this equation looks complicated here, but we can actually rewrite that into a very simple form by integrating it and lumping all these contributions of turbulence into a resistance term, and we end up with a very simple equation here. And in fact, it's a conductance equation where we again relate the flux, here the evaporation flux, to a gradient via, in this case, not a proportionality constant, but a proportionality function here, because this resistance term here, actually, this thermal resistance term here, there's buoyancy in here, depends on the flux itself. So this is actually, again, a nonlinear equation that we have to solve by iterating over it. But in essence, again, it's a very simple conductance equation that captures all the complexity of transport across a rough surface. Okay. So how do we handle this now for vegetated surfaces? So how do we do that? So what we in fact have to do is what we are doing here in our land surface modeling. We basically separate the evaporation flux in two different terms when we simulate vegetation. One term accounts for evaporation from the wet foliage, and the other one accounts for transpiration from the dry foliage. So for the second term, really, we have to take into account processes at the leaf level, so really plant physiological processes. And then we have to, again, upscale them to the stand or the regional scale. So how do we do this? And why do we want to do this? The motivation really comes from observations again here. These are measurements of photosynthetic activity here on the left-hand side over days and temperature. And what you see here is that the photosynthetic activity actually decreases in mid-afternoon. This is called the midday depression, when the plants close their stomatal and stop to transpire and assimilate CO2. Okay, this is because of temperature stress, or for example, also of water stress or nutrient stress. This is also something, for example, we measure over the fields in PhenoRob. And actually, to be prognostic and simulate that, we have to take into account plant physiological processes. So in this case, we split up the transpiration term in potential evapotranspiration and a scaling factor here. This is a scaling factor that becomes very important in a minute. So the question is now, how do we simulate the potential evapotranspiration from vegetated surfaces? This follows our Monet-Bukov similarities theory that we just discussed before. So the flux over the rough surface, depending on the humidity gradient and this kind of, resistance term we have. All the magic sits in the scaling factor. This is the place where we actually inject our knowledge about plant physiological processes related to photosynthesis, related to root water uptake and nutrient uptake. This is the place where we actually introduce our knowledge for upscaling. And this is actually also the place where we can inject our knowledge about management, for example, of agricultural systems like irrigation or fertilization. Okay, so this equation is very benign here because at this point in time we really hide all the complexity in this scaling factor, and we will only let's say look at this kind of superficially. So we just state here that this scaling factor depends on many different parameters and functions. For example, for the upscaling, we use in this scaling parameter, we use the leaf area index for sunlit and shaded leaves. This is also a parameter, for example, that is measured in PhenoRob. And then we introduce plant physiological parameters via stomatal conductance concepts, given here as resistant terms again. And these resistant terms, these stomatal conductance concepts, are directly related to photosynthesis, described here via the assimilation rate, which is depending, for example, on carboxylation, which is part of the photosynthesis, limiting functionals, for example, due to temperature stress, or for example, here due to root water uptake, if we have, for example, soil moisture limitation. So, as I said, this all here, these different terms, they all hide, let's say, the complexity of our knowledge about plant physiological and nutrient processes and management processes at the let's say plant level that we use then to upscale it to the regional level. Okay, so this was a quick tour really from the bottom to the land surface at the edge to the free atmosphere. That's where we stop today. And I would just want to take provide some take-home messages here. What are those? Vegetation, including agricultural plants, are an integral part of the terrestrial water and energy cycle, connecting the subsurface with the atmosphere. And this goes, of course, in both directions. The processes act on all time and space scales and are strongly nonlinear. and we need to make major simplifying assumptions, and sometimes also ad hoc decisions related to upscaling and on how we implement the physical and geochemical processes. And we always have to keep in mind these assumptions and decisions we make. But the terrestrial modeling is really a useful tool to understand two-way or nonlinear feedbacks and establish the past and current state that we call reanalysis of the terrestrial systems. And we use these tools really to interrogate impacts of human interventions and make predictions.